Good morning, everyone. My name is Nurul Farhana binti Muhammad Yazid. My group partner name is Nur Kistina Alia binti Misri. And we will present our project title, Design Improvement and Analysis of Hand Trolley. Next, we go to project objective. There are three objectives in this project. One, baseline evaluation. Conduct a static structural FEA on a 8-part hand trolley to map height stress zones and isolate the critical to plate. Second objective is design optimization. Stimulate the three independent updates. Gasset reinforcement plus material shift, lightweight pocketing, under thermal loading, and topology optimization. And lastly, third objective is problem resolution. Resolve how structural mess can be reduced without compromising factor of safety (FOS) and evaluate how temperature change alter stress propagation. Next is introduction. Finite element analysis, or it's calling FEA, is a simulation method used to predict how a product behaves under loading condition. For this project, we use ANSYS software to analyze the hand trolley product by calculating the deformation, total deformation, von Mises stress, and factor of safety (FOS). The scope of this project includes static structural analysis, material optimization, thermal analysis, and topology optimization. However, dynamic loading, buckling, and nonlinear failure were not included in this study.
Okay, look at this flowchart analysis. So first step is type, and we go to the CAD solid geometry generation. The 3D model is constructed using CATIA V5 and exported into a standard size step or STP format to ensure smooth data transfer between software. And we model import in F4. The geometric model is brought into the analysis environment to begin the simulation setup. Second, for FE setup for analysis environment, this step we define the physics, material behavior, and constraint of the system. Material property definition and material assignment with specific engineering material, for example, steel, aluminum, or composite, are assigned to the component, defining their mechanical properties like Young modulus, Poisson ratio, yield, uh, ultimate strength, or tensile strength. For assembly interface contact, we define how different parts in assembly interact with one another, for example, bonding, sliding, and frictional contact. For global mesh generation, the solid geometry is discrete into the small element for numerical analysis. For the setup, specific the node limit that we show is 17800, and ensuring computationally efficiency or adhering to a specific software limit, license limits. And next, we apply boundary grounding constraint and static force vector to implement real world condition by fixing certain phase or point in surface grounding and applying the relevant operational load force vector operation. Next, structural solving. This phase is execute the core mechanical simulation. So the execute baseline mechanical static analysis solver, like static structural F5. The analysis solver process the linear static equation to determine how the model react under the applying load. Then next is for isolate total deformation, von Mises equivalent stress safety factor at solution I6. The primary engineering output are extract to evaluate the structural integrity of the baseline design. Then we go to optimization and design improvement. After analyzing the baseline, the project branched into the three distinct optimized parts to improve the performance of analyzed environment factor. First is branch one. Branch one is for effect of material type. That's testing how different material composition alters stress and deformation behavior and safety factor. Second is improvement one. Improvement one, we combine with effect of temperature difference, and that evaluate the impact of thermal stress and expansion on the structure. Next is improvement two. We using the generative algorithm to remove material for lower stress area, reducing weight while the maintaining structural integrity. So for this improvement two, we combine with the topology optimization. We use the improvement two to get the topology optimized part. In the topology optimized part, we just focus on the load platform only. So we change the parameter and change the design because we show the topology from that. Okay, next is post-processing and conclusion. This is the final stage, validate the design modification. So extraction of quantity data and the post-processing optimization verification. The numeric data from the three improvement part is gathered, compare and verify to confirm if the design objective was successfully achieved. And last is end. The simulation workflow is complete, yielding and optimized design ready for reporting or manufacturing.
Geometric model and product dimension. This picture is a drafting assembly of hand trolley product that we choose to analysis in analysis. So in this product, the height of this product is 137 mm and the width of this product is 300 mm. Next, this slide show of the engineering drafting of assembly exploded and the bill of material of hand trolley BOM. The complete model was designed using the CATIA V5 software before being imported into the analysis software to analysis. The assembly of this hand trolley part is consists of 8 main components. They are the holder, load platform, handle, support triangle, support wheel, screw, and nut. Each part was modeled individually and then assembled into one complete product. Beside that, engineering drawings were prepared to define the dimension of every component accurately. This is our first part, that is handle. And this is five of the 8 main parts. That is screw.
Okay, for our project, we choose to design and analyze standard hand shortly. We built the entire 3D model using the software called CATIA V5. Think of this slide as showing our digital twin or virtual prototype. Building the trolley on the computer first is super important because it lets us check if all the pieces fit together perfectly. And like we constrain each other part, and if the sizing is right, and if there are any mistake before we waste any money building a real one. Okay, this is our design by each part. So we can see some of the individual part we create before putting them together. We have standard hardware part like the hex nut and bolt that hold everything together. Then we have the custom part like the rubber handle grip for the user, the main axle shaft that hold the weight and the wheel for the movement. And we also have the what you call support triangle and support wheel to connect for each other part. And we have a load platform to bring to create to put the object and the load at there. So the making this separately is used for two reasons. Firstly, it's let us give different material to different parts, like a rubber for the handles and steel for the bolts when we test it later. And second, it's let us print out easy blueprints for a factory to manufacture each item. So for the setup, for the FEA setup, to simulate real world condition is our virtual testing lab. We had to carefully set up our boundary and load inside analysis software. For the context, we told the software that the main structural joint are completely bond together, like real weld metal, while the connection between the wheel and the axle use a frictional contact with the friction coefficient of 0.15, so the wheel can realistically rotate. Okay, next, we apply our force a heavy 1,500 Newton payload push straight down on the loading plate, simulating a heavy is 153 kilogram box, where with 0.02 megapascal of pressure vector on the handle stimulate and operator tilting the trolley backward. We also add the thermal temperature change of 70 Celsius to test how well the trolley handle harsh, hot environment without warping and jamming. So finally, to let the computer calculate of this, the trolley smooth geometry was broken down in computational mesh made of three 3x722 tiny tetrahedral element connect by Ec 1955 metaelement not more. allowing the software to check the exact stress level at every tiny corner of our design.
Next is the baseline performance before improvement. The original design was tested under a load of 1,500 newtons. So from the simulation, we can get the maximum 1 meter stress is 183.32 MPa. The maximum total deformation was 2.933 millimeters. Meanwhile, the factor of safety was 1.36. Although the design was still considered safe, the safety margin was quite low. So the highest stress occurred at the connection between the load platform and the frame. This indicates that the joint is the weakest area and needs improvement. This figure shows the maximum equivalent 1 meter stress of the hand trolley product before the improvement. In the red region represent the highest stress. That's it, 183.32 MPa, while the blue one represent the lowest stress. These figures show the maximum total deformation. At the region, we can see the highest region is the red color represent the highest total deformation. That is 2.933 millimeter, while the blue one is the lowest total deformation. And for this figure, it shows the minimum of factor safety, FOS. The minimum is 1.3638. That it shows the low tendency of failure of this hand trolley before the improvement. Next is design improvements, thermal and material analysis. For design improvement 1, we decide to increase the handle thickness from 3 millimeters to 5 millimeters and change the material to aluminum alloy. This is because the modification can help to reduce the maximum stress to 160.67 MPa. Other than that, we can also improve the factor of safety to 1.52 and reduce the total weight to 5.4 kilogram. Next, we study the thermal effect by applying a 70-degree temperature difference together with the mechanical load. Due to thermal expansion, the material experienced the additional internal stress, so the maximum stress increased to 228.58 MPa. The total deformation become 1.0923 millimeters, which means the structure expanded slightly because of the higher temperature. The factor of safety decreased to 1.244 but is still above 1. So the hand trolley is still considered safe and remains within the safety limits. For this figure, it shows the equivalent 1 meter stress for the entire hand trolley assembly after the improvement 1. So in this figure, we can see that the stress is distributed through the whole structure and the highest stress is concentrated at the critical region. That is, the max of the equivalent stress is 160.67 MPa. On this figure, is focused only on the handle. So it give a closer view of the stress distribution on the improved handle, allowing us to clearly observe the effect of increasing the handle thickness from 3 millimeters to 5 millimeters. On this figure, it shows the total deformation of the entire hand trolley assembly. The deformation represents how much the structure bends or displaces when the load is applied. For this figure pula, it shows the total deformation only on the handle. It helps us observe how the improved handle responds to the applied load after the modification. For this figure, it shows the factor of safety (FOS) for the entire assembly. The result indicates that the improved design has a better safety margin and is suitable for carrying the applied load. Lastly, this figure focuses on the factor of safety (FOS) only on the handle. It confirms that the handle is able to withstand the applied load safely after the thickness was increased.
Okay, for the effect of temperature, that we know the overall von Mises stress across the entire hand trolley when exposed to temperature change, and the main frame remains completely blue is that a lower stress, proving that the expansion and the construction from the temperature change do not hurt the main structure. And for the this load platform, a close-up view of the structural stress concentrated on the improvement loading platform under the thermal loading. So the maximum stress rate indicator, the construction right at the bottom back corner fillet where the plate is joined, but the rest of the plate distribute the thermal energy safely. Okay, so this figure for the maximum total deformation for assembly. So the how much the entire trolley warp and physically expand due to the temperature effect, and the structural frame stays stable, but the outer tip of the plate loading plate undergoes the highest displacement in the red zone because it's expand freely outward. So for we focus to the load platform. So for the load platform is isolates detailed view of the physical expansion on the 10 mm loading platform. So the deformation increased linearly from the back wall at the blue contour to the very front edge is the red contour, confirming an informed and uniform and highly predictable thermal expansion profile. Okay, for this is a safety of factor. So the safety margin of the design under combined mechanical and thermal condition, even with the environmental heat or cold add to the mix, the main joint and frame maintain a completely safe structure, dropping slightly on the high stress connection point but remaining well above critically threshold. So the minimum safety of factor is 1.344 something, and there is low tendency for failure. But it's near than one. So maybe okay, this figure show the plot about entire loading plate is solid blue, meaning it easily reaches the maximum safety score of 5 or 15. The only tiny drop happened at the inner corner joint where the metal bend, but even there, our lowest safety score is 6.95, which is still way higher than the standard target of 1.5 and prove the design is completely safe. Moving on to our design improvement 2 and material analysis result. This slide highlight how we successfully optimize the trolley to be both lighter and safer. So for improvement 2, we are engineering the flat loading platform by thickening it to 10 mm and introducing a geometric pocketing pattern to shave off unnecessary mass. This modification successfully dropped the structural stress level to incredible low 1.0042 megapascal while maintaining a steady factor of safety of 1.5. Is we call it low tendency for failure. In tandem with this geometric change, we analyze the material effect by the sweeping out heavy standard steel for a smart combination of aluminum alloy, stainless steel, and high strength alloy steel. This material upgrade drastically reduced the total weight of the assembly down to a highly portable 5.5 kilogram, while simultaneously managing our internal load by safely lowering the master maximum stress to 181.5 megapascal. Okay, next we go to the new material properties table. Okay, so this slide introduce the specific engineering properties of the new material we selected for our optimized hand trolley assembly, which replace our initial heavy stainless steel. In this new configuration, which introduce aluminum alloy, which have much lower young modulus of 68.9 gigapascal, making it highly flexible and incredibly lightweight to help drop our total assembly weight down to just 5.4 kilogram. So next, we use stainless steel, which balance structural stiffness at 193 gigapascal, with excellent durability and rust resistant for real-world use. Finally, we integrate high-strength alloy steel for the critical load-bearing zone with a massive tensile yield strength of 655 megapascal. This ensures the most heavily stressed part of our trolley can handle top force without permanently wrapping or bending. Okay, next, to evaluate the structural integrity of our design, we analyze the von Mises equivalent stress plot instance analysis, which help predict ductile material failure by tracking internal stress distribution, as shown by the color contour transitioning from blue to red. The peak stress do not distribute evenly, instead they localize specifically and the sharp radius. So geometry transition and weld junction where the loading platform meets the vertical phenomena known as stress concentration or stress riser, where geometry discontinuous amplify local stress by implementing our design optimization. Thickening the loading plate to 10 mm and smoothing out this critical junction, we successfully uh, suppress this peak localized tears well below the material is strength, preventing microscopic crack indentation and long-term structural fatigue. Okay, next we go to the max total deformation. So we can evaluate the construct to study how the assembly physically flex and shift is subject to the operational 1,500 Newton payload and the 0.02 megapascal handle pressure. The displacement gradient reveal the maximum deflection, highlight in red, occur the absolute feather extremities of the structure, namely the tip of the horizontal loading plate and the top loop of the handlebar handle from what we call in the light platform. So the naturally experience the highest bending moment, resulting the greatest elastic displacement. So however, our post-processing data confirm that the absolute displacement value remain exceptionally small and well within the acceptable structural rigidity tolerance, ensuring the trolley remains stiff and stable during operation. So for the looking at the factor of safety (FOS) floats, the loading platform display a uniform solid rate profile which the corresponding to the numerical value of 15. In analysis workbench, post-processing tool a safety factor value of 15 representing the maximum default limit displayed on the standard color legend. Indicate what we call indicate a highly conservative engineering state when the structural safety factor is equal to or greater than 15. So when FOS is greater than 15, that across that entire geometry domain. Okay, looking at our final post-processing result for the new material configuration, the von Mises stress plot confirmed that internal load are safely distributed, keeping the maximum stress cap at a low 181.58 megapascal, with most of the structure remaining in a relaxed blue state. And next, for the for the total deformation part, indicate highly controlled flexing, where the only visible elastic movement occur as expected at the outer cantilever tips and a loading platform, where the cargo rests. So for new material, the plot demonstrates excellent structural margin, maintaining at overall minimum factor of safety of 1.52, while the primary loading plate achieved the maximum value of 15, proving that our material upgrade have created an exceptional, strong, stable, and durable assembly ready to industrial operation.
Next is a topology optimization. A topology optimization routine was executed to minimize global compliance under an explicit mass retention constraint of 80% material was removed from low stress zones along the neutral central axis of the plate, producing an optimized organic geometry that maintains necessary load paths. On this figure, we can see the equivalent 1 meter stress after the topology optimization. We can see that the stress is concentrated only in the main load part, while the low stress region have been removed. In this figure, we can see the total deformation after the topology optimization. Although some material was removed, the deformation remains within an acceptable range, indicating that the structure is still stable. Lastly, this figure shows the factor of safety after topology optimization. The results show a higher safety factor, which means the optimization design is still safe even after the reducing unnecessary material.
Alright, everyone. Welcome to the final showdown. Let's look off the data to see how our engineering wizard try completely transformed this hand trolley. Check out the comparative performance bar chart at the top. Our original baseline design was a complete disaster. It was carrying a massive stress of 232.4 megapascal, flexing by 1.42 mm and sitting at the sketchy factor of safety of just 1.07. That means if a butterfly landing on our cargo, the whole thing was at risk of permanently wrapping. But look at the last bar of the last graph topology optimization. Absolutely destroyed the computation. It achieved a mind-blowing 88.27% drop in stress and boosts out factor of safety by astronomically 756.797 75.97%. It's basically strip all away all the lazy and utilize metal and turn the trolley into a lean, mean load bearing machine. However, for the real world manufacturing, we are officially recommending Design Improvement 1 as our champion. Why? Because it offers the ultimate engineering balance. It slashed our internal stress by 50.26%, double our safety margin to comfortable 2.42, and the best part chop the assembly weight for the back breaking 12.4 kilogram down to a featherweight 5.40 kilogram. So to wrap up our conclusion, look at the comic illustration of our two factory friends. The guy in the yellow heart hates and is smiling because his back doesn't hurt anymore. Every single project objective has been completely crushed thanks to Anis's workbench. Our thermal material geometry and topology optimization are fully validated and ready for the real world. Thank you for watching. I'm now ready for any question you, the lecturer, have. Go easy on me. Bye. Thank you.